All right, good afternoon, everyone. Welcome to EfficientML.ai Lecture 7. Today, we are going to jump into a new chapter about neural architecture search. So previously, we talked about pruning and quantization, which all works on existing model. Right? You train AlexNet, you train VGG, you train SqueezeNet, you compress it, you prune it, you quantize it, right? But can we design a small and compact model to begin with? That is our goal, and we are going to discuss that in today's lecture and also next lecture. So before jumping into the lecture, I want to show you our new course website. So the link is still the same. You can access it through EfficientML.ai. That is the single point of entry. And then the schedule, we have a schedule tab right here where you can find the whole lecture schedule, and also you can find the slides. We updated the slide link, so you no longer need to apply for permission. Everyone can just click the slide here, the video for both recording types of recording, and also the lab will be right here. So today, lab 2 is just released. So you can click this button to access the lab, which will lead you to the Google Colab. Open with Google Colab, which you can start doing the lab here. Okay, so with that, hopefully the new website works for everybody. If you have any questions, shoot us an email. So today, we'll talk about neural architecture search, starting from reviewing these basic primitives for deep neural nets with efficiency consideration. Following that, we'll introduce these popular building blocks and then introduce both the manual design and also the automated design using neural architecture search. So the goal of neural architecture search is to find the best design point to balance all of our design goals. So let's just brainstorm a little bit. What is an efficient neural network? And what are the characteristics we want to ideally have for a neural net? So there are several dimensions that cannot be fit at the same time. We want a model to run fast, very low latency. For example, recently, the GPT-4 released this kind of new interface. You can interact it with audio, but the latency is really long. You wait for 5 seconds, 10 seconds, and then you can hear back from ChatGPT, right? So you want to have short latency. If you have a long latency, you might have already hit a car in front of you for self-driving neural network, right? So latency matters. Also, throughput matters. You want to process hundreds of videos on YouTube. You want to process to see if there's a copyright issue. You want to auto caption the YouTube. So throughput matters on the data centers. And also accuracy, that's the first class citizen, right? If the accuracy is bad, no matter how fast it is, how energy efficient it is, it's not helpful, right? So accuracy certainly matters. Energy also matters. Training neural net is computationally intensive, very costly. Buying GPU is hard. GPU is in shortage these days. Like each A100 node is about $160K. Each H100 node ranges between $250,000 to $300K. That's super expensive. So, and also that's the cost. And also to support these machines, recently I've been upgrading the server in our lab. So previously we have 2 plugs. Each plug is pretty thick. It's like this thick, like your hand. Super thick plug. We have 2 of those plugs. I guess how many servers they can support? 10 servers. And now we want to try to switch to A100. You guess how many nodes we can support with A100? Each plug can give you 50 amps, 250 volts, 50 amps. Only 4 nodes if it is A100. What about you upgrade to H100? Only 2 nodes. one super thick plug, 50 amps, can support only one node of H100, so consuming a lot of electricity. And that's why these GPUs are so expensive to rent on AWS or GCP or Azure, because some of the cost is going to paying the electric bill, right? And imagine in the future, everyone is throwing a lot of compute. It's going to hit our world, right? So as MIT students, we want to have the responsibility to protect our world with green AI, right? So we want to make it energy efficient. And also storage. Like many of you have a dream of entrepreneurship. You wanna create your own app with AI capabilities inside, AI inside, right? Building those apps, you definitely don't want to throw a 175 billion parameter model in the App Store. If IP16, how large is that? 350 gigabyte. How long would it take a user to download it? It will drain your whole month data quota immediately, right? So storage matters. For another scenario, like over-the-air update. If you drive a Tesla, the model is updated every time, frequently. You don't have to go to the dealer, but the model is updated by this kind of over-the-air update, which is also utilizing the LTE bandwidth. So if the model is too big, hard to store them, hard to transmit. And when you are doing distributed training, the gradient size is proportional or the same depending on the precision. We just approximate by using the same size as the model size, right? The gradient size is equal to the model size. So if the model is pretty big, then you have to transmit to communicate a lot of gradient between each node. So the state-of-the-art, off-the-shelf InfiniBand system you can buy give you 400 gigabit per second. If each GPU has such a node, such a NIC attached to that, you have 8 GPUs that give you 3.2, so 400 times 8 gigabit per second, right? But if the model is huge, even that may not be enough. And buying those equipment is expensive, like $1,000 to buy each each wire, right? So it's hard to achieve from all these aspects. But we do want to find the optimal point, depending on which one matters more to you, the cost, the social impact, the availability, and everything, right? So we can imagine manually design the model is hard. So that's why we want to learn about neural architecture search to use the machine to design this neural network architecture. Put it in another way, use AI to design better AI. Okay? So let's get started with our journey. Before talking about this neural architecture search, let's first introduce how human designs neural nets. And imagine we are the person. So we start with these primitive operations, just like when you are building your architect, a real architect, building a building, right? What are the basic primitives? You have concretes, you have blocks, you have. So what are those basic operations for neural net? We're going to learn about that. And classic building blocks. Those are the primitives we use to design neural nets manually. Following that, we're going to talk about how to use machines to design these machine learning models using neural architecture search. Okay? What is the search space? How do we design the search space to narrow down? Like you are trying to find your friend in a big forest, you don't want to have the entire map, but you want to narrow down to an optimal search space, to narrow down the search space. And the search strategy, how do you find the good model? So that will be in this lecture. And in the next lecture, we are going to cover efficient and hardware-aware NAS, including performance estimations and hardware-aware NAS to efficiently search an efficient model, and also zero-shot NAS to efficiently search a model. Okay? And also how do we search the neural network, and also the hardware architecture that accelerates these neural networks at the same time. And finally, we'll talk about a lot of cool applications by using NAS in natural language processing, in generative models, point cloud, and also pose estimations. Okay, so let's start with the basics, the foundations of primitive operations. This is a recap since we introduced them in the first lecture, in the introduction lecture, which is lecture 2. So I'm going to go with them relatively quickly, starting with fully connected layer. So we know we have an input, and this is input channel is Ci, output channel is Co. The matrix is Ci by Co. So we can calculate the max. Remember what is a max? Multiply and accumulate. Each add and each multiplication is considered one max. Multiplication and accumulate. So the linear layer is C in times C out amount of max with batch size of 1. So for convolution layer, depending on if it's 1D or 2D, so for 2D convolution, the feature map dimension is h by w, height, width, and also the input channel. And this is the batch size. Similar for the output feature map. For the kernel, you have 4 dimensions: the height of the kernel, width of the kernel, input channel, and also output channel. So that's these 4 dimensions. And also you have the bias equal to the size of the output channel. So we can recap the number of max in the convolution layer, which is equal to the input and output channel, multiply them together, same as here. But now we have the h and w dimension for 2D conv. So we have the h and w for the kernel, and also the h and w for the activation. So this is a multiplication of 6 terms together. To reduce the amount of compute, we introduced group convolution, okay? Group 1, group 2, so that rather than CO times G, rather than CO, now we have the C divided by the number of groups. So the number of weights is reduced by G. In this case, the number of weights is reduced by 2. And similarly, the amount of MAC is also reduced by G times the number of groups. So among different groups, group 1 is no longer impacted by group 2. Like these output channels only depend on these input channels rather than those input channels. Another extreme case is basically depth-wise convolution, where the number of groups of a group convolution equal to the number of channels, so that we completely eliminated one of the dimensions. Like here, if the G equal to here, if the G equal to Ci, okay, so Ci divided by G will be equal to 1. So we no longer have that dimension. So rather than having four dimensions, now we only have 3 dimensions for the kernel. We only have the kernel height, kernel width, and also the channel. So in this case, each channel only depends on the input channel corresponding to the same channel number. It's no longer dependent on other channels. So that's the depth-wise convolution. And the number of compute for depth-wise convolution is basically multiplying these 5 terms rather than 6 terms together, since the number of group equal to the number of input or output channel. And finally, we have this 1-by-1 convolution, where kh and kw are both 1. So we can reduce it from this general convolution to make kh, kw both equal to 1. Then we get these 4 terms, which is the MAC to compute 1-by-1 convolution. Okay, so using those primitive operations, we can construct these classic building blocks. So a building block consists of several layers, and people put them together in a smart way to balance between the accuracy and also the compute. So we are going to visit some of the most classic designs, including the ResNet building block, basically the residual block, the inverted bottleneck used in MobileNet v2, and also the transformer blocks. So this is the classic ResNet 50, the bottleneck block. So this block consists of 3 layers, a 1x1 layer, 1x1 layer, and we have a 3x3 layer in the middle. So why we don't have just one 3x3 convolution and that's it? Why do we have, or are we stacking 3 layers together? So let's see. The 3x3 convolution is much more expensive than 1x1 convolution. Actually, how many times more flops if the channel number is the same? 9 times more expensive, right? So we want to make sure before feeding to this 3x3 convolution, we want to reduce the channel number so that the number of MAC is reduced. So that's why we are reducing the number of dimensions by 4 times from 2K to 512. And then we do this 3x3 convolution and finally expand it back to 2K so that we can continue to add this to the main branch. So the number of MACs in this way, we can calculate it by multiplying these terms together. So for this 1x1 convolution, there are basically 4 terms, HW, input channel, output channel. Okay? We are reducing the number of channel from 2K to 512. And then for this 3x3 convolution, kernel height, kernel width, that's 9, H and W, 512 by 512. And finally, we are using another 1x1 convolution to project from 512 to 2K channels. So putting them together, the total number of MAC is 512 by 512, HW 17. Compared with just using a naive design, just one 3x3 convolution, what is the number of MAC in that way? So imagine if the input and output channel are both 2K, then the total number of compute will be 9 by 2K by 2K, H and W, right? Which is actually 8.5 times larger than using this kind of bottleneck design. Bottleneck means the middle channel is smaller. Let's also calculate the number of parameters. Okay, so 1x1 convolution, the number of parameters is equal to input times output channel number. And this is 3x3 conv, 9 times input channel, output channel, 1x1 conv. Altogether, you have this amount of parameters. What if we don't use this bottleneck layer? If I have a 3x3 conv, that'll be input channel, output channel times 9, which is another, again, 8.2, 8.5 times reduction in the number of parameters. So why we care so much about parameters and MACs? Because that matters with respect to our efficiency. So you want to be super familiar how to calculate the MACs, how to calculate the number of parameters as a first order approximation for your efficiency. And later we are going to see the number of parameters and also number of MACs doesn't directly translate to efficiency. But it's important to be able to do a hand calculation to do first order approximation. So next, you might address next, which further improves the efficiency by introducing this grouped convolution. So rather than 128 channels by 128 channels, res next divided by 32 different groups. Okay, so each group has only 4 channels. So So 4 channels times 32, that is exactly equal to 128. So you still have the same dimension, but here we're having 32 smaller convolutions. And finally, you can concatenate them together, stack them together, and pass it through a convolution that project from 128 to 56, 128 to 256. So the dimension is equivalent. But the difference is here where the convolution here doesn't interact with the convolution over there. These convolutions are independent rather than having a big normal convolution. And since these are linear, we can basically trunk this 128 by 256 by 32 times. So each one has only 4 to 256. And altogether, we can have such very regular 32 paths. And the final dimension is 256 channel, which is equivalent to the original design. So that's the principle of res next using grouped convolution. And the quest for efficiency never stops. Later, people designed mobile net, targeting, deploying these neural networks on mobile phones and mobile devices, where you want to have the model to be small in the number of parameters, so it's easier to upload to the App Store. So people introduce this depth-wise convolution. So each channel, so here we have 5 channels. So each channel doesn't interact with other channel. You just directly run a 3x3 convolution that map the input channel to the output channel, followed by a 1x1 convolution that mingles among different channels. In this case, the blue channel becomes a blue channel. There is no interaction between the blue and the green. But this 1x1 convolution serves as the messenger. You can imagine it's a messenger that mingles all these channels to the output. But it has no spatial modeling capability. Spatial modeling is purely done by this 3x3 depth-wise conv. 1x1 is just mingling the information among different channels. So that's why it's called depth-wise separable block. Okay, you separate the functionality by 3x3 depth-wise conv, which is responsible for spatial modeling, which is separate from its 1x1 convolution, which is responsible for modeling the channel dimension, mingling different channels. So this depth-wise convolution is also an extreme case of group convolution where the number of groups equal to the number of input channels. So let's calculate the number of max and also the number of parameters in this case. Suppose we have n input channels. We run it through a 1x1 conv and cast it to 6 times n channels. We want to expand the number of channels. And the reason is that 3x3 depth-wise convolution doesn't have enough capacity. To compensate for the capacity, we have to increase the number of channels. So this is called the inverted bottleneck, because previously when we are learning the bottleneck, 3x3 regular convolution is very heavy. Therefore, before that, we want to reduce the number of channels. But now, the 3x3 depth-wise convolution is very lightweighted. The number of parameters is less. You lose one dimension. So we use this inverted bottleneck to enlarge the number of channels so that we can compensate for the loss of model capacity. So that's why here we are projecting from n to 6n before this depth-wise. And depth-wise convolution preserves the number of channels, is still 6n after that. And finally, we use another 1x1 convolution that projects the number of channels from 6n back to n channels. So let's calculate the number of max. Original channel number, this is borrowed from the MobileNet v2, which is a very popular, very classic neural net. The number of MACs equal to the input channel, output channel. So we project the number of channels and increase it by 6 times, called the expansion ratio, times H and W. In the middle, we have 960 channels. So the number of MAC is just 960, H and W times 9, since we have a 3x3 convolution. Finally, we project the number of channel from 960 back to 160 times H and W. Altogether, this is the amount of compute. Again, we can compare that with just using a one layer of 3x3 convolution. Input channel, output channel is both 160. So their ratio is roughly the same, slightly more compute. And here is the number of parameters and slightly more parameters. Okay, so later people actually find rather than using 3 layers, where you are going to have 3 different activations to keep in memory, it may be better just use one single dense layer, regular 3x3 convolution. So in 2016, 2017, these depth-wise layers are super widely used. But later, as time passed by, especially with the advancement of high parallelism hardware like GPUs or DSPs, less and less depth-wise convolution is used. But this kind of regular, just normal 3x3 convolution is more efficient. It is better, it can better take advantage of the parallelism in the hardware, and also the compute is more regular. So depending on different hardware platform, different building blocks are preferred. So not always depth-wise convolution or MobileNet is efficient. And actually, sometimes they are super non-efficient. So we dived deeper into analyzing the inference and training statistics of MobileNet v2, especially this inverted bottleneck layer. The number of parameters. So this is compared with Reason 18 with MobileNet v2 scaled it by 3/4 to make sure they have the same ImageNet accuracy. So the number of parameter size is reduced by 4.6 times from ResNet to MobileNet. This is great. However, if you look at the peak activation size, since weight is not the whole world, you also care about the activation. The activation didn't decrease, but it increased by 80%. Peak activation is not equal to the total activation, but the input activation plus the output activation, which is what we have to put in the AI chip. And you can guess why this inverted bottleneck is leading to even larger activation, even though the model size is much smaller. So compared with the ResNet, which is using the bottleneck, this is using the inverted bottleneck. Look at this, 6N, right? The number of channels is increased by 6 times compared with the original number of channels. What about bottleneck? It decreased by 4 times, and altogether differed by 24 times. So does that impact the number of parameters? It's linear, right? So the number of parameters is linear proportionally to the number of channels. Since it's a depth-wise layer, the number of parameter is just 3x3 times the number of channels. What about the compute? the compute is also proportional, right? So they're okay, but the thing is the activation, right? The peak activation, you don't care the smaller channel, but you care about the biggest one, which is the bottleneck, right? So here you enlarged the activation, and therefore you have to maintain a larger buffer if you want to put all this channel in the on-chip SRAM, right? So this is something we have to solve. We're going to talk about that in the MCUNet lecture. So this is about inference. How about training? During training, the number parameter is not the bottleneck, but the activation is the bottleneck. So here we are assuming batch size of 16. Since usually during training, you don't use batch size of 1. You use batch of a pretty big certain amount of batch size. So the activation becomes the bottleneck. Although the number of parameters is reduced by more than 4 times, the activation, the total activation, not the peak activation, the total activation only reduced by 10%. That is again due to this inefficiency in the inverted bottleneck, where you have to expand the number of channels. So if you only care about number of parameter, this is great, 4 times smaller, right? But depending on the scenario, either for inference or training, if you care about the activation, this is not the ideal solution, right? So there's always not the best of both worlds. That is a consistent thing we have to deal with in neural network design. That was make it beautiful. It's hard, but all right. So people continue to explore what is a good trade-off and invented this ShuffleNet. What ShuffleNet is doing is basically very similar to the ResNet and also the MobileNet. They are having 1x1 conv and 1x1 conv in the beginning and in the end. This is actually very similar to the ResNext, where they're using the group convolution. Like here, you have 3 groups. The first group, the feature only is only dependent on the first input group. But the problem of this group convolution is that different groups, they never talk to each other. There's no information flowing from group 1 to group 2, group 1 to group 3, group 2 to group 3. So ShuffleNet introduced this shuffle operation, where the first channel takes certain part from the first group, some part from the second group, and some part from the third group. So now the first group can see both group 1, group 2, and group 3. Similarly for the second group and third group. So by introducing this channel shuffle, each group has 3 colors, rather than previously each group has only 1 color. That encourages the information flowing between the groups. So it gets the best of both worlds to reduce the cost by using group convolution, but also it can encourage this kind of information exchange among different groups by this channel shuffle operation. And this channel shuffle operation needs to be efficiently implemented, since you want to avoid the data movement. But luckily, there is no arithmetic operation. There's no MAC, no compute. Another important building block is the transformer, and also which is built from this multi-head self-attention. Let's first ignore multi-head. Just assume we have a single head. What is a self-attention? So we first project our vector into query, key, and value. These are different when you have multiple head, but for one head, you have 1 query, 1 key, and also the 1 value. So the basic operation is you first project your input vector by multiplying with the Q matrix, key matrix, the Q matrix, K matrix, and also the V matrix to a projection. And from the efficiency perspective, you can merge these 3 matrix vector multiplication or matrix depending on the batch size into one larger matrix multiplication by concatenating the Q, K, V matrix into one larger matrix and then multiplied with the input vector. And the basic operation is we first calculate the Q, K transpose. Imagine the Q is of dimension n by d. N is the number of tokens. D is the hidden dimension. I can imagine this is the number of words. This is how many dimensions do we use to represent each word. Put it simple. And after transpose, the dimension becomes d times n. So by multiplying them together, you get n by d attention matrix. And we want to scale it because if the hidden dimension is larger versus smaller, we don't want the attention map to look different. So you want to scale it by dividing it by the square root of the hidden dimension. So you get this n by n attention map. And you use this n by n attention map to linear project the Q, the V matrix, okay, the V matrix in yellow. And finally, you get another n by d result. So the computing complexity is n squared d. N squared d plus n squared d is roughly O(n) squared. So even if you use flash attention, you can make this linear, but the compute complexity is still O(n) squared. And this is a visualization of an attention map. So the sentence is about the video game is a lot more fun than the film. Assuming each word is a token, this is a real attention map. Like we can see, video is highly attended to game, and also game is highly attended to video. So this kind of attention map makes sense. And finally, we have another output projection matrix. So before that, we concatenate all the heads together. And just now we talk about one head QKV projection, dot product attention, output projection. Okay? And if you have multiple heads, you will just concatenate the results of different head before passing it to the linear layer. So this is the basic building block behind the large language models in ChatGPT. We are going to revisit this in the large language model lecture. With that, we concluded talking about these basic operations and building blocks. Let's take a 5-minute break, and then we are going to introduce neural architecture search. Let's continue our discussion about neural architecture search. So there is a pretty big design space. Like we mentioned, in a neural network, we have to design many dimensions, like the number of layers, number of kernels, kernel size, number of channels, connectivity, resolution. So using human expertise, this is such a big design space where we want to leverage this machine to design machine learning models to automatically find those good dimensions. And we can find this trade-off without and with neural architecture search. We can clearly see the difference. So previously, these are handcrafted models, including the ResNet we just introduced, which has a pretty large amount of max with decent accuracy, versus the MobileNet, which has a smaller amount of computation, well, still pretty good accuracy. So we want to ideally push the frontier to this low MAC area and also the high accuracy area. So we can see by these dots with the asterisk in the middle, those are auto-designed model architectures, which clearly has an advantage over these manually designed models by having smaller compute and higher accuracy. So here are the components for neural architecture search to achieve that. Right? The goal is to find the best neural network architecture in a search space and maximizing our objective, including accuracy, efficiency, etc. So we start with a search space and then define a search strategy propose an architecture, then we evaluate the performance, the performance estimation, including the accuracy, the latency, the energy, etc. And we use that to get a feedback to our search algorithm, which can propose the next architecture we are going to evaluate. So in today's lecture, we are going to focus on these two, the search space and search strategy. In the next lecture, we will focus the performance estimation and also hardware efficiency considerations. So let's start with the search space. We're going to talk about cell level search space and also network level search space. And we'll start with cell level search space. So a neural network has many building blocks. Each block, we want to find the best architecture of them. And you can simply, one simple strategy is that after you search one cell, you can repeat the cell by n times and construct a neural network. You're just repeating these cells, including a normal cell and a reduction cell. So reduction cell basically reduces the resolution. So these are two examples of the searched normal cell and also the reduction cell. Compared with the manual design models we just described, like MobileNet, ResNet, these NAS design modules are pretty complicated. It takes the input from both the previous layer and the layer before the previous layer. It can have many different choices. It can be separable 3x3, identity layer, separable 5x5, average 3x3, and lots of different choices. And these wires are very complicated, creating a lot of dependency. So the machine design model is hard to be understood by human. This provides pretty good accuracy, but unfortunately, the dependencies are so complicated. It's very hard to efficiently map it to hardware for efficient inference. For example, you cannot release a buffer until all the dependencies has been finished. So it requires more memory footprint than actually needed. So what it does is basically starting with several components. Okay, you have a RNN controller. At each time step, we emit several choices. The first choice is what is the first hidden state you are going to use. Okay, since one operator needs two operands, and what are those operands coming from? So in this design, it can either come from the previous layer or it come from the previous layer. So you have the first hidden state, the second hidden state, both of them have two choices, finding these two inputs. And then we want to select the two input transformation operations. For example, here, we can do a 3x3 convolution. We can also do a 2x2 max pooling. Finally, we need to select the method to combine these results. Like we can do add or we can do concat. So the right-hand side is the generated cell as one example. And this is the process, how it was generated. You're basically using a recurrent neural net, and each time step, you're emitting one of the choices. So imagine in this case, let's just calculate how large the design space is. Suppose we have two candidate inputs. So here we can choose from the previous layer or the layer before the previous layer. And here we have n candidate operations to transform each input. Then we have n potential operations to combine these two states. So what is the size of the search space if we have B layers, assuming each layer is independently searched? You have two candidate inputs. You have m candidate operations and n operations to combine them. So for each layer, actually, you have to first choose the first state. You have two choices. You have choose the second state. You have two choices: first layer or the previous layer or the previous layer. M operations and also N methods to combine them, and then you have B layers. Multiply them together to the power of B. So this is the design space. And assume M equal to 5. Say you have 3 by 3 convolution, 5 by 5 convolution, average pooling, indented layer, etc. You have 5 such choices. N equal to 2, you can do either the element-wise add, or you can do the concatenation. These are very realistic example. And we have 10 to the power of 11 candidates in the search space. That's pretty big. And after finding each individual block, we want to have this network level search space. Okay, we already find each cell. How do we combine them together? So that is the network level search space, including the depth. We can have depth of 2, depth of 3, depth of 4, etc. The depth dimension. We also have the resolution dimension. We can use a 3 by 128 by 128, a smaller, pretty small resolution, or we can go with a larger resolution, like 256 by 256. So this is another dimension we have to choose. We also have the width dimension. We can choose between like 384 channels, or 512 channels, or 768 channels. And for different blocks, we can choose different number of channels. So that's the width dimension. We also have the kernel size dimension. So we can either use 7 by 7, pretty large kernel, or 5 by 5, or a pretty small 3 by 3 kernel. So you may ask whether can we always use 3 by 3 kernel? What is the pros and cons? For example, 2 3 by 3 layer versus 1 5 by 5 layer, assuming the number of channels is the same. They both have the same size of the receptive field, right? 2 3 by 3 versus 1 5 by 5. What's the advantage of having a single 5 by 5 layer? So yeah, you have more number of parameters. Then what is the advantage of 3 by 3 convolution? It has smaller model size, right? That's the other way. What about the activation? Imagine you are doing training. Now you have 2 layers if you need 3 by 3. So you have to store 2 copies of the 2 layers of activation. But now you have only 1 layer. You have only one layer of activation. So this will require less amount of GPU memory to store those activations. So that's why it's hard to tell whether we should use 3 by 3, 5 by 5, or 7 by 7. 7 by 7 may even have larger parallelism. So we just should like the neural network search algorithm to find the best search space. Just give you all the candidates, all the possibilities, that you give me the best solution.
There's some intuition as to why we pick 2 layers at a time and find them in some way. Like try to avoid.
No, this is just empirical. You can have 3 layers, 3 things, or you can have 4, or even more complicated. That's not necessary to, or why do we find n or n minus 1 layer? That's also a matter of design. So that work is very pioneering, but also has a lot of limitations and assumptions.
A priori, if I'm understanding correctly, we're picking layers and then like a connection, finding the results. That's one architecture.
It's not the whole design space. Definitely not the whole design space.
Whole, I mean, in some sense, yeah, I'm missing something. In some sense, doesn't seem like it's natural. works well, but is there some intuition for why we do that rather than, let's say, building layer by layer?
So this is considered one cell, which consists many branches, right? And here you can transform. You have two inputs. That's pretty natural, right? You add two numbers, you multiply two numbers, or concatenate two chunks of activation. So you have two operands. Maybe you can have three, like adding three elements. So I think this operation is natural to have two operands, and each operand you want to do some transformation, right? So 3x3 count, 5x5 count, or average, 3x3 average, or identity, or 5x5 separable convolution. So I think it's pretty intuitive.
Okay, so each of those cells is a subset of a layer.
This is a subset of
You
a.
don't have two full layers. You'll apply one operation on half of the inputs and another operation on the other half.
So skip connection is included here. You can have identity. So if both of them are identity, then basically this is a skip connection. Right, so let's continue. So we talk about the kernel size, the depth, the width, the resolution, and also there's a topology connection. Usually we need to downsample the neural network to get a lower resolution so that you can have a larger receptive field and also reduce the computation. One approach is basically you downsample and upsample. This is probably the most natural way. You go from 224 to 224, and then 112 by 112, and then 56 by 56, and 28, and then 40, and then 7, and then you upscale it in the same way. That's probably the most natural way. So this piece of work basically look at what are the total, what is a larger design space and give you more degree of freedom. You can downsample, upsample, downsample, upsample twice. You can downsample a little bit, stay the same resolution, and then downsample, and similar for the other side. Or you can just downsample, stay the same, downsample, keep the same resolution, never go to an even smaller resolution. So every time you have several choices. You can continue downsample, you can keep the resolution, you can upsample, which can make it into a grid where you have many different choices. As long as the final result you reach this point, for example, during image generation, you give the image, you want to generate the image of the same resolution. So no matter how many times you downsampled and upsampled, as long as the final resolution is your input resolution, that is good. And therefore, each path along the blue node correspond to a network architecture. On the right-hand side are three possible architectures. And some of them are quite widely used, including DeepLab v3, the UNet, stacked hourglass. So we have different representations, different dimensions to search. And as you can imagine, this is a pretty big search space. We just calculated it's 10 to the power, pretty big number. So we want to narrow down the search space. You don't want to search in a full search space, but using some heuristics, some smarter way to be able to narrow down to a smaller search space. So you're constrained within a smaller space so that we can perform this resource constraint model specialization. We call it TinyML from our prior work. And the motivation is that when you are trying to deploy neural nets into these edge devices like phones, microcontrollers, IoT devices, there are many different constraints, latency, energy, or even the memory constraint. So there are a lot of models designed for mobile phone, like MobileNet, but there's no prior work, a lot less prior work designing models targeting IoT devices. Mobile phone can easily have like 4 or 8 gigabytes of memory, but these IoT devices only have a few hundred kilobytes of SRAM and 1 or 2 megabytes of flash. So how do we design a model to fit such tight memory constraints? Like on this microcontroller, it has only 320 kilobyte of SRAM and only 1 megabyte of flash, compared to a phone has 4 gigabytes of memory and more than 64 gigabyte of storage. So this is comparing the memory for a GPU, a phone, and also an IoT device. And you can tell this is a pretty tightly constrained scenario. And there's no prior art. How do we design the model for that? So it's like a blank piece of paper. And how do we narrow down the design space? So we want to design the design space for TinyML. As you can imagine, training the model is expensive. You have to train the model for a while, so it's hard to use the accuracy to approximate whether a model is good or not. But a simple heuristic we mentioned is that computing is cheap. Memory data movement is expensive, right? So given the same amount of data movement, assuming the memory, given the same memory, if a model can have a larger number of flops, it indicates it has a larger capacity and more likely to achieve higher accuracy. So without training, we use that as approximation. So same memory constraint, what is the maximum amount of flops you can fit into that memory? And that is our heuristics. So we generated different design spaces, color them into different color. And here the design space means the width and also the resolution. Like for a tiny microcontroller, should you use 160 or should you use 224 resolution? That's hard to decide. So we put that in the design space. And whether should we shrink the model by to its only 30% or 70%? That's also part of the design space. And for different design spaces, we plotted this curve between the number of flops versus the cumulative probability to achieve such flops. What is the percentage of the model that can achieve that flops? For example, this black one is a pretty bad design space compared with this red curve. Why is that? With 80% of probability, this design space can have a number of parameters more than 50 million parameters. Well, this one has only 32 million parameters. So give the same amount of memory footprint, this design space can return a much higher flops, more degree of freedom, and also more capacity compared with this black design space. So here is 80%, here is 20%. So those top 20% of the models has number of flops greater than 32 million, while this top 20% is greater than 50 million. Okay, so apparently this red design space is better, which has the width of a half and resolution of 144. And indeed, when we evaluate the accuracy on this good design space, the best accuracy is 78, compared with this one is only 74. You can, in this design space, you can have many different designs, and you can easily calculate the flops. We show the calculation. You just multiply the 6 terms for convolution, 2 terms for the FC layer, so you can very quickly tell what is the flops. Right, exactly. It's very cheap. You don't have to train it. Otherwise, if you use accuracy, you have to train the model. It's pretty intensive. All right, so indeed, compared with other heuristics, the narrowed design space indeed rendered a pretty good accuracy after the search. It's even better than using a much larger, huge search space, but given the fixed amount of search time, it cannot achieve good results. Or compared with this random search space, is pretty bad. Versus this is Ryzen 18 at 224 resolution, which doesn't fit the memory constraint, which is out of memory, but we want to show our search model fitting such a very tight memory constraint, only a few 100 kilobyte of SRAM, can meet pretty much get very close to the standard Resident 18 at 224 resolution. But random sampled design space and huge design space lead to worse accuracy. And here we show the number of flops is a good approximation of about the final trained accuracy, which is very almost linearly correlated. And we want to choose the space corresponding to a larger number of flops that can fit this limited amount of memory. So indeed, this verified our approximation using the flops to search and approximate that with accuracy. And the rule of thumb is computing is cheap, data movement expensive. So if you can use the same amount of memory, but do as much computing as possible on that, that is considered a good design space.
So the different architectures that you listed, they essentially impose constraints of the factors.
Right. They all share the same constraint. You have to be fit within that like 128 or 256 kilobyte of SRAM.
So there are different ones with the same amount of memory that accommodate different problems. So is that because the architectures impose constraints relative to the height?
Right. They have different resolution, different width. Okay, so having talked about the search space, now we switch gear to talk about the search strategy, including grid search, random search, reinforcement learning, gradient descent, and also evolutionary search. Grid search is the simplest one. Like here, we want to search between the width and also the resolution. The resolution has a design. This is a design space for the resolution. This is a design space for the width. If you have only 2 dimensions, this becomes a grid. Okay, that's why we call it a grid search. You just want to define a step size, like every increase by every 10%, 10%, and then you're going to sample each grid to measure the latency and also the accuracy. Some of them break the latency constraint, some of them meets the latency constraint. As you know, this is a pretty brute force. You have to try each case. And another scenario comes when you have already designed one model, say a model that has 10 million parameters given 80% top line accuracy, but I want to design a larger model that give a higher accuracy. Since there are so many pretty big design space, I can either make the model wider, make it like wider, but same depth, or I can make it deeper compared with the original model. I can make it deeper, but the same channel number of channels, or I can scale the resolution, make the input resolution larger, or I can combine them all, make it a little bit wider, a little bit taller, and a little bit higher resolution. So people find you should not go to the extreme for only one dimension. For example, if you want to enlarge the model by 2x, 2 times larger, you shouldn't just rely on just one dimension, make it much wider to meet that 2x target. You cannot just make it 2x deeper. That's also not the best case, or increase the resolution only. But this kind of compound scaling, people find it the most helpful. Okay, scale both the height and width dimension, including the resolution dimension. So here, if you want to enlarge the model by 2x, and we want to enlarge the depth, width, and also the resolution, remember the depth, the total compute is linear to the depth, power of 2 to the width, and also resolution. Remember, we have that earlier this lecture. And after the enlargement is equal to roughly 2x, we can search this alpha, beta, and gamma, and to find what is the optimal one that gives the best accuracy latency trade-off. If you want to find a different size of the model, not necessarily 2x, maybe 3x or 4x, we can just control this phi. So this gives you the a very good insight where compound scaling is helpful. Don't just tune one dimension, but tune them all together. But how exactly do we search? We can use grid search and exhaust a lot of a large design space. Of course, Google has a lot of TPUs, but of course, we want to find a smarter way with better search strategy, not only the grid search. A very widely used method, a very simple method is random search. Actually, we want you to experience this in your homework. Grid search basically have this very regular pattern in this grid. Search everyone, everyone, everyone. Random search, you can use less samples, but if you're lucky, you get a pretty good design. But why do we use random search? This is basically to you can do a soundness check, just eyeball checking, just give a rough estimation. Make sure after a few iterations of random search, your reward is getting better, your loss is getting smaller, right? If everything stays the same, it's likely your code implementation is wrong. So whenever we are trying to search something, we usually start with random search and make sure the loss is decreasing, showing that our implementation is correct. Basically, this is for sanity check using random search. Also, people have been using reinforcement learning to choose different actions. Okay? For example, previously we can sample an architecture using the recurrent neural net, choosing the number of filters, choosing the height, width, stride, etc. Lots of choices. So that consists of making it into action space. And then it can sample architecture by having all these choices. Then we can sample architecture with probability P, and then we train this child network to get accuracy R, and then calculate the gradient of this probability, because the gradient of other components is not differentiable, but this gradient of this P, this probability, is differentiable, and scale it by R to update the controller. And next time the controller is going to emit a new architecture, and on and so on. So basically, use reinforcement learning as a sequential to make the sequential decision, and it trains this controller to choose the best architecture. And you can imagine this could be very slow, because each iteration, in order to get a reward, you have to train the model to get the accuracy. Another way is to use the gradient descent, which doesn't require so many iterations and a lot more computing efficient. For example, different paths, you can have 3x3 count, 5x5 count, identically different choices. Say you have 3 choices. So what do? We try all of them 3 with probability alpha, beta, gamma, right? We have 3 choices. And we try to make this differentiable so that we can train this probability. And finally, at inference time, you choose the path that has the highest probability. For example, choose this thickest blue curve and thickest red curve. What is the drawback of this approach? You have to keep all choices in memory. Like you have 3 choices here, alpha, beta, gamma. You have to keep 3 copies of activation, enlarging your GPU memory a lot. Therefore, people tried to search on small data set, like Cypher data set, and then use the search model to transfer it to ImageNet. Otherwise, the GPU memory will explode, since you have to put all different choices, candidates in the memory. So this is showing the softmax about the alpha, beta, gamma different probability sampling from the probability, and use that as a weighted average of different output paths. We can even make latency differentiable, right? So we want to search a model not only accurate, but also run fast. So this is our work. We also have alpha, beta, gamma, etc., which is a probability to sample each path. We can pre-measure the latency of each building block. Since they are static, we can measure the latency offline. Okay, so in this way, if the path, the probability of sampling each path is known, then we can have the expectation of the latency. And we can define the loss as not only the cross entropy loss, the regularization term, but also this expected latency. And we can back propagate the gradient back to its alpha, beta, gamma. Okay, so that we can take latency, also make latency differentiable, so that we can create end-to-end search strategy to balance between the accuracy and also the latency. Another widely used approach, actually we are going to implement that in the homework, is evolutionary search, borrowed from biology, where we have a population, we have a design space, we can randomly sample a point, a design point. We have a function that calculates the fitness. Fitness in here, we can define it as the number of max, number of model parameter size, or the accuracy, or a combination of them all. And then we can do two operations, crossover and also mutation. We're going to talk about that soon. And then select the best fit, and then repeat this process. For example, we can have a big network. We select, sample a subnetwork, and see is it fast enough. If it's good, then we keep it. Otherwise, we resample by mutation and crossover, and repeat this process until we find the best one. So what is mutation? So given a neural network, we can mutate on the depth. For example, 3-layer versus only first layer here, or 3 layers in the second stage versus 4 layers in the second stage. So this is mutation on the depth. We can also do mutation on the operator. For example, used to be a 3x3 convolution, now it is a 5x5 convolution. Or previously it's a 3x3 convolution, now it becomes a 7x7 convolution. We can do a crossover. So we have two candidates that has been mutated. One is mutated on the depth, one is mutated on the width, or the choices. We can do crossover. Okay, so this is after the mutation, this is before the mutation, and each one we can randomly choose between the unmutated versus the mutated one. Right. So here, both of them are the same. So 3x3. Second one, we come in from parent 2 from here, and the next layer after the random sample, it comes from parent 1. So it's blue. It's a blue block. And so after mutation crossover, we can select the best fit as the parent of the next generation, and repeat this process until we find the best model. Okay, so that's concludes the neural architecture search, the search strategy. In the next lecture, we are going to talk about hardware-aware NAS to efficiently search efficient models. Using graph, you can certainly treat it as a computing graph and apply some graph neural nets on top of it. Since graph neural net can extract the relationship in a node that is pretty far from it. But here, it might be directional graph. Yeah, it might be acyclic. So there might be some constraint on top of it. You don't want to repeat, or sometimes you want to repeat. Yeah, can be cycle or acyclic, either way. All right, thank you. That's all for today's lecture.